All right, so we're going to go over, I guess, what would be our third spectroscopy that we've got covered in this course. First two were Raman and infrared spectroscopy, right? And this is called photoelectron spectroscopy, often abbreviated as PES. And this can be used to determine the energy levels of molecular orbitals, which is why we are particularly interested in it in the context of, the surprising results that we just saw for methane, where we had 8 bonding electrons, 4 single bonds, but the bonding electrons were in 2 different molecular orbitals with 2 different energies. 6 of them were in triply degenerate T2 molecular orbitals, but the other 2 were in even lower energy A1 molecular orbital. So let's see what we can do with photoelectron spectroscopy to kind of probe the electronic states of methane and other molecules. So like in most spectroscopies or many spectroscopies, you're going to bathe a sample in monochromatic light, so light of one wavelength. And what can then occur is ionization. If that light has the correct wavelength, right, you're going to eject electrons, essentially making cations. So let's say you have the energy, the energy, the wavelength of light you use, so you know the energy of the photon that you use. Where is that energy going to go? Some of it is going to be in the ejected electron, right? So you ionized it, and that electron is going to have certain kinetic energy. That's going to be embodied in this value here. Some of it, though, is going to get absorbed by the binding energy, basically House ionization energy, right? And then also some vibrational energy that maybe causes some excitement to a higher vibrational state. And so what wavelength of light you use can really dictate what electrons you are probing. And so if you use ultraviolet light, this is light of relatively low energy. This is called UPS, or ultraviolet photoelectron spectroscopy. Typically, this is for valence electrons, okay? So you're not going to be ejecting core electrons because the light just doesn't have enough energy to get to those core electrons. However, if you use higher energy X-ray light, right? X-ray is the spectrum that's adjacent to the ultraviolet that has more energy, lower wavelengths. For X-ray photoelectron spectroscopy, XPS, this will give you information about core electrons. I should note that in this course, we're only going to be talking about UPS. UPS is really what's important for bonding, right? Because valence electrons are those that are involved in bonding. So valence electrons, UPS, probes molecular orbitals. XPS doesn't usually give you any information about molecular orbitals, but it is very useful for other things. It can be very useful to detect what elements are present in the sample, irrespective of bonding, right? Because now in XPS, you're only probing core electrons. So who cares if you're carbon dioxide or carbon monoxide? XPS can help you figure out if you have carbon and you have oxygen, right? And so from a materials science standpoint, XPS is far more useful, generally speaking, than UPS. But from a chemistry standpoint, UPS is more useful than XPS. So in years past, I have taught a material science course that we've gone over XPS and other spectroscopies and other techniques, analytical techniques in materials chemistry, as a materials chemistry course. I might be teaching that in the near future. I don't know that far ahead for you guys, but that's something that if you're interested, it was a lot of fun and a really good class. So anyway, we got this formula, and we know that basically the binding energy is similar to the orbital energy. That's essentially saying that the binding energy is equal to the ionization energy. And so I just subbed that in. Orbital energy there, and then the apparent ionization potential, I moved ejected electron over to the other side, so we got E photon minus E ejected electron, and what I'm calling the apparent ionization potential, that is going to be equal to the E binding or the E orbital plus vibrational, okay? And so what you're going to get here, what you're plotting, is you're going to plot the apparent ionization potential versus the number of electrons. So you're basically going to have a detector at the end of your system, and you're going to measure the energy of the ejected electrons. There's lots of detectors that can do that, measuring kinetic energy essentially. And you know E photon because you have monochromatic light, and so you can get this value, which is E apparent, very easily. And so that E apparent is E binding plus E vibrational. If E vibrational is 0, there's also E rotational in here, okay? That's usually a smaller effect. Then, you know, these terms, obviously, E vibrational goes away, E rotational goes away, and so you end up with just E apparent. And a typical plot looks like something like this. We'll just call it intensity now, but it's really number of electrons detected by your detector. And this is ionization potential. And this can be increasing ionization potential, or the arrow can be going the other way. So you just have to, you know, look carefully at your x-axis. It will be labeled, or it should be labeled, right? But both plotting conventions are used, so you just have to pay attention to that. But what's, you know, apparent here is you see all this fine structure. This is one, you get one big peak in this case. We're only talking about one molecular orbital here. So you get one big peak, but you get all this fine structure. And the fine structure is from the vibrational states, right? And so the way to think about this is, you know, we talked about vibrational spectroscopy, and this is, you know, part of the reason why I start out with vibrational spectroscopy, so we can understand, you know, these other concepts and appreciate them more fully. But we talked about vibrational spectroscopy and how we can approximate this with a harmonic oscillator. I'll just call this, you know, E1. It's like electronic state 1. This is, you know, maybe ground state, right? So you're down here in the ground state, and maybe you're at nu equals 0 at the ground vibrational state within that. And there's some, you know, probability IR light gets absorbed and you go to nu equals 1. Or maybe if you have an overtone, you go to nu equals 2, right? But what you're doing now is now you're shining UV light at this thing. So it's much higher energy light than infrared light, which we did in vibrational spectroscopy. And now you're actually going to another different well, right? You're changing the electronic configuration. I don't know, maybe you had some molecular orbital diagram that looked like this, and now you shined UV light and you went to an excited state like that, right? And so now what happened? You still have this second, I'll call it E2. This is the excited state, right? And the excited state has its own harmonic oscillator, right? And it has its own potential well. And so what's going to happen when you shine UV light into it is you could be going, let's say you're just going from the ground state, you could go to the ground vibrational state of the excited state, or you could go to any of these different excited states, right? And that's what's giving rise to all these small peaks. You're actually probing the vibrational fine structure of that excited state harmonic oscillator well, okay? And so this point here is called like the 0, 0 point. This also can have rotational structure. Hopefully in PChem you're learning about this, right? Which in each vibrational state, there's also rotational states. Those are typically accessed using microwave spectroscopy, microwave light, right? And so that's why you have so many here, okay? It can be rotation and vibrations there. And 0, 0 basically says when you're at the ground rotational state in the ground vibrational state, okay? But you still got to an excited state of electronic state, excited electronic state, electrons. So that's going to be this lowest energy point here. But all these other ones are excited vibrational / rotational states. The vibrational fine structure is dictated by this same expression that we saw before, right? The frequency is 1/2 pi times the square root of k, the force constant, over the reduced mass. So you will see differences in the spacings, right? Each of these little spacings here, that is essentially this, right? It's the spacing in your harmonic oscillator well. So if the reduced mass, for example, changes, this spacing will go down, right?